We are group 18, consisting of Hampus, Valdemar, Felix, and Olaf. In this video, we'll be conducting a demonstration of the simulation environment we have created. And we will start by showing the parameter file where the user is able to customize the simulation. We will then start the simulation itself and go through some of its features. And finally, we will discuss possible improvements that could be made to our work. At the top, you're able to pick which robots. We have support for 3 different robots, the Kuka, UR10, and Yumi. You can then choose a gripper that is compatible with the robot. The 3 fingers are G6, and Shadowhand is compatible with the Kuka and UR10, while Yumi is only compatible with Yumi. You can then choose some start position, change whether you want the camera or not, and its precision. Continuing into the simulation, we have some parameters as well, such as the step length, whether you want a table or what object you would like, and so on. And then we can continue with the motion from Hampus, I believe.
Yeah. So in the motion, we can. It is possible to set a target for the robot to reach. It is defined in translation and rotation, so we can set a dual quaternion target. Below this, we have the grip path, which is where we have to define a path for a file that we want to use to grip objects. And in this file, we define the joint position during the grip, so the user can customize each grip and change grip through depending on simulation. And at last, we have the graphics, and where we can just change the visual settings to higher quality or lower quality.
Yes, and to use this simulation, we are just going to run this main program called robotsimulator.py. And if we run it, we are greeted with this beautiful ASCII message called Chalmers Robot Simulator. And we make our final changes to the parameter file before we begin, and press enter. And we are now in the PyBullet environment, where we can use scroll and the mouse to move around, very similar to various CAD programs. And to use this environment, we can add a table or put the robot on a table. We are also able to spawn different kinds of objects depending on what we choose in the parameter file. And moving on, we can also take some pictures of it. This one is using Matplotlib to show the image. We can store it if we want, and if we move the robot a bit around, it's very difficult to use it by hand, but we can do some point cloud as well, if we do it like this maybe. Yes, this will be enough, and we can also put a point cloud, generate one. Now this doesn't look very good, but for the different cameras perspective, it has then created a point cloud that we can use for obstacle avoidance and other useful things. And this engine uses, we stitch the cameras from one camera in here in the robot arm itself, and also one in the environment located here somewhere. We stitch those point clouds together using Open3D.
Yes, so we've also made some functions to actually control the arm and the gripper. So we have, for example, a function called OpenGripper, which should open the gripper. Yes, all right. And we also have a function that closes the gripper called grip. Yes, and it does this, like Hampus said earlier, according to a data file, and it can be changed if you want a different grasping motion. Then we also have a button called Enable Joint Control. And this brings up a little panel where the user can choose each and every joint position. And yeah, it makes it a bit easier to get the arm to a desired location. Then we also have a great button called Reset Simulation. So if the user puts the arm in a very weird position, he can always decide to reset everything back to default.
Yes, and as was shown before, if you don't want to use the sliders, you can also control the robot just by dragging it around, making it easier to get to some certain positions. And if we look at the buttons, we have move end effector to target, no plan button, which will move the robot to the custom target that we set in the parameter file. Yes, that will take some time, but it gets there. And more than this, we can also plan custom paths in simulator. So we can, if we take this position and we press get set pose, and we just move it a little bit, and we can save this pose also. And now we can press follow saved poses. And it will move to the first pose. Then after this, it will move to the next pose. And any amount of poses can be added here in a queue to simulate any wanted path. It is also possible to test several grasps, which is the multi-grasp simulation. So in a folder, we have saved several points, dual quaternion points, and if the gripper should grip or not. And if we press this multi-grasp simulation button, it will simulate each of these, and then it will reset itself, show the next path, and then it will reset itself and show for each file that has been added to this folder. And this gives the user the ability to test several grasps in one time without having to restart the simulator.
All right. So that were our functions that we implemented. But as with any project, there are always improvements to be made. So Valdemar earlier showed a very nice point cloud. And that's very useful data when you want to do more advanced stuff. So for example, if you want to plan the motion for the robot arm and maybe consider obstacles, then you could use this point cloud data to plan those movements. And as of right now, if you want to combine the arm with a gripper, you need to actually manually merge the files. But yeah, a function for this would be desired. But we believe we've made a good basis to test and implement more functions and also to help with further research. So yeah, we want to thank you for listening to this little demo and thank you for your time.